All right, we're going to walk through Merkle trees and the algorithm. It's in the notes. There's a nice graphics. The code, there is pseudocode for you to follow. And I'm actually going to walk through the pseudocode. So the first step is convert blocks into leaves. Of type, each leaf becomes a type of slice of byte. And since we have a whole bunch of these, this is going to be a slice of byte. And we're going to call this HTMP. That's what we're going to call it. And then for each one of these, which means I'm going to have a for loop. So there's a position and there's an H of HTMP. Okay, so we're going to iterate through these things. We're going to create leaves. Now you've got to allocate the space for the leaves, or at least declare it, and then you can append. Okay, so what is my output from here? We'll call this HMid. Equals append of HMid. And we want to take the hash, which is hash.hash of something like that. I'm just going to call it H here. And we're going to do htemp sub I. Now, each time append appends, it appends from the current position to the next one, so you have to allocate this so it has 0 things in it. When you get done, a good check is to make certain that HMid has the same number of things as HTemp. When I developed this code, I certainly put a test in there to validate that. The third step is where we're going to start working through our tree. Now, we're going to come back to this step in a loop. We're going to loop here. But we're also going to have an inner loop because our outer loop is walking down through the levels of the tree. Whereas our inner loop is walking across the things in the tree. So there's 2 nested loops in here. Now, the inner loop is done, and in fact the whole routine is done when our output is down to 1 node. We have a root node, we're done. So we want to take ln, this is really before we start 3 here, we want to take ln is equal to the length of hmid. Okay, then we're going to loop, and I see no particular reason to have limit the number of levels in our loop. It's decreasing by half each time, so just a for loop. Loop forever. And for each one of these things in HMid, we want to calculate the next level down. So we want to start out with HTMP equals append of HTMP, and we want to take hash, but here's where we get into trouble. If we have an odd number, let's say 3, then we want to take the first pair and do that one separately. So we want to work these in pairs, okay? Not as individuals, and we've got to go across over here. So before we can do this calculation where we're going to create this, we've actually got to go and do another loop because we got to walk across it, and we need to have an empty htemp at this point. So something like htemp equals make, and what do we want this to be? The same thing it was before, a slice of byte, and we want it 0 long up to ln divided by 2 plus 1. So that'll be big enough for all of them, whether it's even or odd. Now, I want to walk across these in pairs, so I'm going to do a loop that increases by 2 each time. And I am not real certain of what condition you want here. I'm going to put a little question mark beside that. That depends on how you write this. And I have seen this condition, I have seen II plus 1 less than ln, I've seen a variety of things there. But that depends on how you implement it, okay? So I'm just going to underline that with a question mark. This I'm certain you want. How you test that you are getting to the end of your loop is up to you. And then you want to find out if you're on an even one, if II plus 1 is less than ln. If you do it that way, I don't think you want that. We'll just take that out. This is an even one. You have a pair, so we want to do h temp equals append of h temp. And what do we want to append to it is the hash of two things, which is h mid sub II and h mid sub II plus 1, because we've got two things to do. Else, we want to do h temp equals append of h temp, and we just want to do 1. H sub H mid sub II. And then we want to end this loop. That's this guy right here. Now, at this point, if, we come out of the bottom and h temp's length is 1, that means we're actually done. So, if len of h temp we want to return h temp. We've finished. Okay? Now I'm running out of space there, but the only other thing is a squiggle. Nope, there's one other thing you have to do, and then I'm going to draw a line for where we can put that squiggle that I didn't put in. And that is really that you do h mid equals h temp. And you have to recalculate that guy right there, the length. So that's got to go down there too off the screen. And then you come back around to the top of your for loop. So there's a couple pieces down there. It's in the notes. But if you walk through this, what we're doing is we're saying, as long as I have at least 2 of these things out here, I will do 2. If I've only got 1, I'll just do 1. And when I get down to the point where there's only 1 left, I'm out of there, I'm done. I've calculated it. Now, doing that this way means that you have just a pair of loops, and you're just going to manipulate everything as bytes as you go through. It's really obnoxious to have to debug bytes, I give you that much. But you just manipulate it as bytes, everything works out. And the only place you have to do any conversion is going from blocks to our original bytes, and then you just sit here and iterate down through the levels of the tree. The tree gets smaller and smaller each time. That's a good check to put in your code. Is when I'm testing, what did I make certain of? That the size of h temp was less than the size of h mid at each level when I iterated. I put in a print statement and verified that in construction. Okay. That's kind of the detail walkthrough of the algorithm for the Merkle trees. And this approach, just a function that just calculates it in this way, is fast and short. I think I mentioned this. My solution was 32 lines, and it probably had some print statements in it. I probably could have gotten it down a little bit less. So it's not a long implementation.